Good day. I am Cassandra Enriquez. Together with my fellow members, Giselle, Dala, and Karen Lood, we will be discussing our chosen biomaterial, the liposome. Liposomes are vesicular structures made of lipids that are formed in aqueous solutions. Structurally, they resemble the lipid membrane of the living cells. They have been widely investigated since the 1960s as models to study the cell membrane and as carriers for protection and/or for delivery of bioactive agents. They have been used in different areas of research, including vaccines, imaging, application cosmetics, and tissue engineering. The simplest method of preparing liposomes is hydration of dry lipid. The lipid is dissolved in organic solvents along with any lipid-soluble compounds to be incorporated into the liposomes. The solvent is commonly removed by rotary evaporation, resulting in a thin film or dry lipid. Some solvent can be removed by lyophilization, resulting in a dried lipid cake. An aqueous solution containing water-soluble compound to be encapsulated is then added to the lipid film or cake to hydrate the lipid and form the liposomes. The aqueous solution must be heated above the phase transition of the lipids in order for the liposomes to form. The resulting multilamellar liposomes consist of many concentric lipid bilayers, while all or most of the lipid-soluble compounds will be incorporated into the bilayers of these lipid liposomes. The amount of water-soluble compounds entrapped is usually very low because the MLVs have a small captured volume. Very little aqueous solute penetrates the onion-like layers of hydrated bilayers lipid.
The captured volume of these MLVs can be increased by freezing and thawing the liposomes several times. Repeated freezing and thawing ruptures and reforms the MLVs, resulting in increased number of liposomes with fewer layers of lipid and more aqueous space inside each liposomes. Thus, the freeze-thawed liposomes encapsulate more aqueous solutes and often have a multivascular morphology. The aqueous solute is now uniformly distributed inside each liposomes. The only method which can produce definable unimodal distribution of liposomes in a 100 micrometer range is high-pressure membrane extrusion through membrane-tight filters of a fixed pore size. The stainless steel device, which supports the filters used for extrusion, withstands internal pressure in excessive 1000 psi. Extrusion cannot be accomplished with standard liquid filtration devices. Larger extruders are pressurized by nitrogen, while extruders handling volume less than 1 milliliter utilize gas-tight syringes to generate pressure manually. Extrusion must be carried out above the phase transition of lipids in the liposomes. In order to achieve narrow size distribution, the liposomes must pass through filters 10 times or more. The liposomes suspension becomes more translucent during extrusion, indicating that the liposomes are becoming smaller. The lower size limitable liposomes is 30 to 60 micrometers, depending on the type of lipids used. High shear methods are used to reduce multilamellar liposomes to unilamellar liposomes at their lowest size limit.
The thin film method is limited to laboratory scale, while the reversed phase evaporation can be used to produce milliliters up to thousands of liters of liposomes. Lipid is dissolved in organic solvent along with any lipid-soluble components. The aqueous compound is added to the lipid solution. This biphasic mixture is then emulsified by some form of high shear mixing. The organic solvent is evaporated from this emulsing force, forcing the lipid into the aqueous phase, where it organizes into bilayer and form liposomes. Additional aqueous phase is added in order to complete the liposome preparation. Again, the temperature of aqueous phase must be above the phase transition temperature of the lipid in order for liposome to form. Unlike MLVs produced from a thin film, liposomes produced by reverse phase evaporation usually have one up to a few bilayers per liposome. Like freeze-thawed liposomes, these liposomes can be multivascular.
For the RIPP of liposome synthesis, lipid is the starting biomaterial used, and it is dissolved in the organic solvent. The mixture will then undergo rotary evaporation to produce dried lipid film cake. Next is the addition of aqueous solution containing water-soluble compounds and will be brought to heat to produce multilamellar liposomes. The multilamellar liposomes is then freezed and thawed to increase the captured volume. After that, the liposomes will undergo extrusion through a membrane-tight filters of fixed pore size. The extrusion process is repeated 10 times to achieve narrow size distribution. Lastly, the multilamellar liposomes will undergo high shearing method to produce unilamellar liposomes.